Welcome to the Internet of Things. This is a bit of fun Internet of Thing. It's a longboard. It's powered by an Arduino controller. It's got a 2400 watt power supply. WeChuck does 28 kilometres an hour, has a range of 10 to 15 k's. In Christchurch, it can be quite exciting with earthquake damage to the roads and the footpaths, and also acorns. Acorns will throw you off this. I have instructions from our R&D manager to always wear a helmet when riding it. So, control it with that, throttle with that. Welcome to All Your Device Belong to Us. How many of you note the slightly esoteric reference there? Badly translated Japanese video games? Cool. So, welcome. My name's Bryn Lewis. I'm a devices guy. I work for a company called Wynyard, which does software for detecting the financing of terrorism, money laundering, corporate risk management, forensic analysis of devices which are seized in police raids, and large-scale police investigations. I also work for an organisation called Sensing City, which is putting sensors all over the Christchurch area. And the other sideline, I work for a company called Pocket Vouchers, which does online promotions in the hospo industry. So, how many of you have texted in a code off a Carlsberg or a Hagen package in the last couple of months? Right. Your chances of winning are pretty low. There is one person who drank 102 dozen Hagen during the duration of the competition. Very dedicated and passionate about their pursuits person. So, today we're going to talk about some things. We're going to look at some things. I've got a shed load of gear on this desk. I lost a day out of my life yesterday debugging the demos. The IT guys and the presentation team guys have been marvellous. They've put up with me, and hopefully everything should work. I've got 8 devices on the stage, and I'm going to put 2 devices out into the audience. So things are going to go really, really well, or it's going to be a train wreck. Judging by the previous presentations I've been to, it's going to be a train wreck. If the keynote fails, it's not good for the person who's doing the demos in the room on the far side of the road. So, we're going to talk a bit about connectivity. How do you connect your devices up into the cloud? We're going to talk about some hobbyist cloud services. Some of you, no doubt, will want to try this stuff at home. We're going to talk some professional cloud services, which is where Microsoft's offerings apply. We're going to talk about my hobby, which is Code Club. I'm one of the founders of Code Club New Zealand. We run Code Clubs all over New Zealand. I'll talk a bit about that at the end. And then hopefully we'll have some time for some Q&A. And we might do some demo runs on the longboard if people are game. This room here is not the carpet. You get a bit of a bow wave going in the carpet, so it mucks you up. But we might try it outside. Not on the hill, though, because 30 kilometres down Hobson Street could be fairly exciting. So, we're going to talk about the Internet of Things. And I'm not going to talk solely about devices. I'm going to talk about the politics and the social acceptance of this technology. People care. Users care. You don't want to wind them up. The people who are using these systems want you to be responsible with their data. Now, how many of you have written an app which, if it went wrong, could kill people? A few of you. My first app out of university was a blood bank. We checked units of blood for AIDS, hepatitis A, hepatitis B, hepatitis C, and syphilis. Any one of those could spoil your day, and one of them could spoil your day an awful lot. My next step after that was building software for power station control management, synchronous generators and switch yards. And if you're having a conversation with the product owner and you say, "So Baldrick, what happens if we open the wicket gates, we've got the inlet valve open and we lose oil pressure?" You know it's going to get really ugly when the product owner's response is take steps, big ones upstream. The other thing with switch yards is you never point. You don't go, "Oh, look," because 66,000 or 120,000 volts will come quite a way to get you. The whole safety critical thing is something that will be ignored until someone is killed. In Germany, a couple of weeks ago, a couple of technicians were killed by a robot in a factory. Someone started it up without getting everyone away from the machine. It's going to be a problem, and much like quadcopters, fireworks, all of those sort of things, there will be a minority who screw it up for the rest of us who are responsible. So pay attention, make sure your apps are well-behaved and good citizens. So customers like the Internet of Things, but they don't like some bits of it. So they don't like you not telling them what you're going to do with their data. They don't like you not saying who you're going to share your data with. And the customers really don't like the fact that you can now cross over from their virtual world into their physical world. Knowing someone's search history and popping up adverts based on that is sometimes useful, sometimes a little bit invasive. Imagine what happens if now your search results and search adverts are based on things in your real world, like what's in your fridge, the temperature of your house, the humidity of your rooms, things like that. Customers really, really don't like you monkeying with their data in ways that they are not aware of. So we've got some challenges coming with this technology. We've got millions and millions of devices, and there's huge money flowing. The latest estimate, the different commentators, Gartner, Forbes, people like that, are all sort of leapfrogging each other with the massive, massive money involved. The last one I saw was it's going to be a $14.4 trillion marketplace. You've only got to get 1/10 of 1% of that, and you're home and hosed. But I'm sort of wondering, the amount of effort that people are putting into this, it's an awfully big trough, but there are a lot of people trying to get their heads into it. And it'll only take one person to poison the marketplace for everyone else, one very public failure. A German steel factory was compromised 3-4 months ago. They were held to ransom, and then hackers hacked their SCADA system and destroyed the furnaces. Imagine that happening at someone's house. Their power smart meter gets hacked, suddenly the lights are going on and off. It's actually being used as a weapon. Stuxnet took out centrifuges in the Iranian nuclear weapons program. When states start using this technology, all bets are off. Power grids, smart charging infrastructure, waste, water, it's going to be the opening salvos of any coming war. So, where do these things sit? We've got them around your person. We've got Fitbits. We've got smart watches. Inside your building, monitoring room temperature, humidity, lighting, even the lifts even the escalators across the way, which start as you walk towards them. Transportation, we've got instrumentation of trucks and monitoring of their usage, the temperatures of the cargo. I was talking to someone who wanted to monitor acceleration of their packages because they were having their product damaged in transit. So we put a small data recorder in based on an Arduino, and it collected acceleration data for the journey. And we found what was happening was the drivers were dropping the boxes off the end of the truck based on the timestamp and the acceleration and deceleration data we were seeing. Airports and railways are all going to be using this technology, so it's going to become the glue which holds our modern society together. One of the projects I'm working on with a school in Amiri next term is a Farm of Things project. We're going to monitor water usage, water application, and then how much power it costs to pump that water up and onto the plants. In a municipal scenario, around the cities, monitoring parking. You've seen a few of the car park buildings, like at Christchurch Airport, where there's sensors about the size of a hockey puck in every car park, monitoring what people are doing. I'm talking to someone about putting transducers and remotely controlling street lamps, turning them on and off based on whether there are people nearby, and then dimming them to save power. For those of you old enough to remember Battlestar Galactica, where they're shooting the fighters out of the tubes at the beginning, I want to do that with a laptop down Memorial Ave and just have the lights coming along next to my car. It's an amazing piece of kit, and it's going to make city councils' lives easier, preemptively fixing things, monitoring water usage. In Christchurch, we have a problem with the drains. Previously, drains which flowed down now sort of flow flat. And because they flow flat, they don't empty and stuff gets stuck, and when your drains back up, it's bad. We had the drains back up in my street. Plumber came, went, "Oh, mate, it's not your drains, it's the street." He went outside and lifted the lid and looked in and went, "Oh," shut the lid. I was relieved. The street I live in has an incline. I live at the high end. The plumber said, "Mate, you don't want to be down the far end of the street. They're going to be having a very bad day." So, energy management. We've got a coming crisis. We're going to be plugging our electric cars in. We're going to get home in our Tesla or our Nissan Leaf or whatever we drive. Any of you car people? I've seen a really nice aerial atom. Someone's got an aerial atom and fitted it with the electric running gear. It looks like a demon toy. I'll just have to wait till my mother passes away because she would hate it with a passion. Now, we've got a problem. All these electric vehicles are going to be charging and they consume a lot of energy, so we need to share the load. We also need to maybe use those batteries in those vehicles to power our houses. So as a house owner, you might go, "Oh, yep, my Tesla's in the garage. Power's getting expensive because it's 6 o'clock at night. I'll run my house off my Tesla for half an hour because I'm not going out tonight and I'll save myself $5. So that sort of active pursuit of best value will become part of the Internet of Things as well. And you may actually dedicate an agent to manage that process for you rather than doing it as a carbon-based machine learning unit. So these things range in size a lot. That's the smallest one I've got. And then I've got a Raspberry Pi, which is a bit of a beast. So that little chip on top of the $quarter, that's a wireless chip. It comes out of China. One minor problem with it, for about the first 6 months, the manuals were in Chinese. But it is surprising how much of a technical document you can reverse engineer when you look at the detailed diagrams and timing and stuff. So we've got a problem. These parts, internet-enabling things, has got to add some value to the customer. So say you're building a toaster. Your China National Toaster Corporation. How much is adding Internet of Things functionality to that worth? It's most probably worth, say, $5 max. You might pay $5. There's a toaster around which will burn into your morning toast the logo of the weather. So your toast pops out and sort of slightly darker in the middle is a picture of some clouds. I thought that was quite cool, but I wouldn't pay more than $5 for it. It requires a bit of hardware to do that. So if there's a standard rule of thumb, which is a 6 times multiplier, a piece of kit which you put inside your piece of kit, it costs 6 times more by the time it gets to the shop. I used to work for a mobile radio company, and we had that rule of thumb. So if you can add $5 to the cost, it means you can add about $1 to the bill of materials. So that means that's actually out of play, that chip, because they're like $6.95 retail, so it's most probably $1. So it's got a picker processor, Wi-Fi, and a few other bits and pieces. So if you're willing to pay sort of $46, you might get that inside a toaster. We've got a problem, though. That little processor can't do much. So how many of you have tried to do implementation of, say, AES and looked at the processor power that requires? It is quite possible, and I wrote down the notes here, to fit an AES implementation into 1.5K of code and 198 bits of RAM on an 8-bit processor. A comment much used by people at this stage is, just because you can doesn't mean you should. Anything involved in crypto is usually fraught. It's going to end badly. Part of the problem is you haven't got enough processor power. You haven't even got enough storage. An X509 certificate, which we all know and love, is about 7.5K for a server cert or 1.4K for a client cert. So that's not going to fit into my Arduino device with 2K of memory. We've got some challenges around that too. Imagine if you've got, say, in my case, 40,000 street lamps, and suddenly your certificate authority is compromised and you've got to replace 40,000 certificates for your products to keep on going. The Internet of Things has a different usage pattern to the human Internet of Things. The human Internet of Things is designed for people randomly clicking on links and looking at cat videos and porn and all sorts of different material. And you're going to multiple different sites, you're pulling down data, you're in the loop, and you can make effective decisions about what you're seeing. If it's got the green with the big tick, you're right, we're in. But a device isn't like that. A device is talking to one thing its field gateway or its server only. It's not wandering the web, surfing videos, anything like that. It's just a single focus device, and there's often no human in the loop. And it'll be making decisions on data and exchanges it has with other servers, so it has to know whether it can trust them or not. So we've got some problems as well as around connectivity. Wired, great. It's good, lots of bandwidth. And you can even use PoE to push power down it, because powering these devices is hard work. You're not going to run a bit farm off a solar panel. Bitcoin farm off a solar panel. These devices run off a flat cell battery. They're $14 for two. But if you write your software right, it'll last for 6 months. I haven't actually got it right yet. The longest I've had is 3 weeks. I've got a funny feeling that I'm maybe not quite aggressively powering down the radio enough. So this little chip on the end is roughly the same size as the Wi-Fi module. That little chip on the end is a Nordic NRF24 module. The small version here's got a range of about 30 meters, and it can send it up to 2 megabits. The device on the thing gaffer taped to the corner of the presenter's podium has got a range of 1 kilometre in clear space. It's pretty good. 32 bytes makes you think. How many of you were at Rob Tiffany's presentation yesterday? Right. Hello, Rob. I'd be worried if you weren't. You made me repitch quite a bit of my presentation last night because you sort of went right through where I was going to be. That device can send 32-byte chunks to up to 256 other devices, which is really good. I worked on a system which used Inmarsat comms, and I smiled when Rob told the story. Inmarsat, it was a cent a byte, and we became obsessive about counting bytes. This is the sort of thing that you end up in the Internet of Things. Even though the number of bytes isn't huge, it mounts. If you've got 1 million devices, a couple of extra bytes counts. I've got a series of blog posts where I take an HTTP request and shave the size down by removing headers, removing server names, dates and times and everything, and then doing some really perverse things by putting the data into doing it as a GET, which is wrong. RESTful people will hate me for it. Putting the data into the headers because that meant I didn't have to have a body. It's really unnatural, and I don't recommend you should do it. But sometimes, just to make the data fit, you've got to. We've also got a problem. These devices last forever. You can't redeploy to your internet toaster out of the end of a continuous build process. These devices don't have the bandwidth. They don't have the comms. You're going to get to see it once, and if you're really unlucky, you might get to see it twice. You can't afford to visit these. And that means you've also got a problem with the engineers and technicians who will see those devices in the field. These devices are stuck on walls. They're the sort of thing that you're never going to touch, hopefully. How many of you have written an application where you've deployed it and not touched it for 15 years? Never. It's a totally different mindset. And we're going to have to get used to it. So what does this mean? For example, how many of you have got a smart TV with some sort of web surfing capability? More frighteningly, how many of you have got a smart TV stuck to the wall of your office, monitoring the output of your build process? Okay, you'll like this. So, this is a smart TV. Came from a reputable vendor. They first shipped them around the beginning of 2012, end of 2011. When they shipped, it had a few bugs, a few CVEs. For any of those of you who are not familiar, they're security issues, 30 or 40. That's cool. It's only going into domestic environments. It's not sitting in an office where you can see it from outside and someone with a Cantenna and an evil twin Wi-Fi access point can take it out. So it has a 1-year product cycle. So they sold it for a year. You could go to Noel Leemings, some other big box brand, and buy it. They then did one software update, ever. At that point, it had 178 issues, CVEs. These guys bought a couple of these TVs, pulled them apart, and examined it to see what open source libraries, what closed source libraries, what processor boards, and all the magic glue that had been used to build the Skype, the YouTube player, the media management system, and all of that. They worked out that it was going to be accruing, based on previous experience, vulnerabilities at roughly half a vulnerability a day. So that meant that at the end of the serviceable life of the TV, it was going to have roughly 2,000 vulnerabilities. So imagine I'm sitting in the car park of your company with a Cantenna pointing it at your build display. My evil twin fires up, your TV connects to it. I then own your TV, and now I've got a beachhead into your infrastructure. And it came out of the TV, which is cool. At home, my personal preference for the bestest possible TV would be one with an HDMI socket on the side, and that's it. Nothing beyond that. If you look at the audiophile stereos, they've got a volume knob, and that's it. There's no bass, treble, no loudness, no nothing. It's just a volume knob. That's what I'd like, because it means I can't, or I'm less likely to be compromised. Problem with functionality is the more functionality you put in, the more your attack surface grows. So, next time you're looking at your build results, think. So, there's going to be a lot of these things. I've done projects with 100 things. I've done a project with a couple of thousand things. I've got software, the beer voucher software, runs inside POS terminals all over New Zealand. We've got 500 or 600 clients in each major city, so all up we've got a couple of thousand clients. It's a world of pain. Every time our POS vendors upgrade, and we've only got to interact with 5 vaguely positive and competent POS vendors, it's a world of pain. The classic one is, oh, it's not working. Okay. We deployed a new PC and it's not working. Okay. After a bit of research, I found that it was set for Californian time, and it was it was set to Californian time zone and New Zealand time, and it had flipped in and out of Californian DST. So that meant that the timestamp on the SSL conversation was an hour out, so the firing went, no, mate, you're alone. It's just simple things like that which will break your systems. You've got millions of devices, gigabytes of ingest, and petabytes of data to process and analyze. And then once you're looking through the petabytes and closest to real time, then there's exabytes of data for post-processing and analysis. You're going to be throwing Hadoop and Power BI and other tooling at it. So we've got some sensors. I've got some demos coming up. So if you've got some different technologies for talking to these sensors, we've got digital inputs, a simple on-off switch. Digital outputs, LEDs, actuators, motors, things like that. One-wire devices like this temperature sensor. This comes from Dallas Semiconductor, and it sends temperature and power down the same cable, and it's submersible and safe to up to 100 degrees. But you want to hitch these to tiny little things. So with this device, I actually turn the sensor on and off when I don't need it. And same with the radio link. You're basically aggressively sleeping all of the stuff around the microcontroller to make sure that you don't run out of power early. You've got smaller things like these devices. This runs on a couple of AAA batteries. And you don't have to be quite so aggressive with the sleeping of this, but it's still pretty painful. You're going to be writing code for these in C. As you step up a level, you might be able to do it in C# or Lua or one of the other different IoT-focused programming languages. When you get to bigger things, it's easier. You can use a proper operating system, some variety of Linux or Raspberry Pi running IoT, Windows IoT Core. These devices can be quite robust, but you've still got to take into account the fact that they will be around for 5, 10, 15 years embedded inside some appliance. So, talking to these sensors. Microsoft are trying to standardize the model for talking to the sensors, and I think it's most probably a good thing. But my kids do quite like the way that the IntelliSense works in the IDE. This is talking to an accelerometer and an Arduino. We've got a library, and the Arduino people are really good at producing libraries and so forth for sensors. I've downloaded it, installed it, I've turned it on. You might be wondering what the serial begin is for. That's for debugging, and we'll talk about that a wee bit later. So you basically create the accelerometer, power it up, start the serial terminal, and then loop round and round and round. The Arduino IDE generates code which wraps around standard off-the-shelf compilers and gives a non-professional developer half-decent development experience. There's a method that you have to implement which sets the device up, and then another one which you have to implement which is called regularly. So then on a .NET micro framework device, we've got C#, Happy Plays, writing code. I actually get paid to write Arduino code and write C# code on NetDuinos for a hobby. So we ensure that we're connected, we create it, we enable measurements, then we read, and then we just loop round and round and round. Then on a Raspberry Pi, it looks like that. Someone's written a library, which is really good, to allow you to talk to the sensors. So the devices themselves. You see us pressing the button. IT guy. Oh, there we go. So the devices themselves, I'm using a Arduino Uno R3 with a ADXL345 accelerometer on it. Actually, I shake all the time. I have overactive beta transmitters. I'm not scared. So these, well, I will be if this demo blows up. So these are all plug and play, and it's great if you want to play around at home. So we've got Arduino Uno R3 with an accelerometer, a NetDuino 3 with an accelerometer, and the one up here is an RPi with an accelerometer attached. So let's see how those work. Hopefully over the presentation, my laptop will get faster as I shut down more of the applications I've got running. Because I've got the Arduino IDE, 2 copies of Visual Studio, and lots. So, PC 7. So here we go. This is the Arduino IDE. I've got a bit of code, and you'll see down here, I'm talking to the accelerometer. Oh, this is actually the code for the device. So I've got setting the radio power levels. I'll just flip to the piece of code I want. ADXL345 test. So I'm setting the gains, setting the sensors up, and then displaying the results. It's pretty much boilerplate C++. There's some pretty nasty C++ floating around where people have hacked up demonstration apps. So serial monitor, COM12 is not available. It's on 13. Here we go. Tools, serial monitor. So there we go. So as I rotate the sensor, you'll see that the G's move around. These sensors were originally created for use in things like airbags and military applications. This particular sensor measures plus or minus 16 Gs in 3 axes. So, works pretty well, quite reliable, and surprisingly low power. So if we shut that one down, next step is my NetDuino. So, wrong instance of Visual Studio. So this is the NetDuino development experience. It looks just like Visual Studio, and it is just like Visual Studio. You can get a plugin for Visual Studio which lets you do Arduino development called Visual Micro. One of the things with Arduino is the bootloader doesn't let you modify the application. So you can't actually debug without re-downloading, and the Visual Micro does that for you. So everything's happy here. So it deploys the binaries to the device. They're interpreted rather than native code. And there is a native code compiler coming, he says, hoping that it starts. Bang. It does take a wee while to download the first time, and here we go. So we're now getting acceleration data out of this device. And you can see as I invert it, the Z goes to negative, go down like that, Z's now 0. They're also used in things like hard disk controllers in your laptop to park the heads when you drop them. They have a series of outputs, so you can put the device into a sleep mode and then sleep the microcontroller attached to it as well, and then use acceleration or deceleration to wake it up. It's also the bit which does the rotation of your screen, and they can also be, they understand taps. So they can provide quite a bit of functionality and offload quite a bit of it from your microcontroller or your PC. So this is where it starts to get tasty. So now I'm running it on a RPi. This is a universal Windows app. It's downloading across the wire. to my RPi. Takes a wee while to start up because it's got to download a bunch of stuff, and I'm hoping that it's finding my network connection. We struggled yesterday. The DNS was unhappy with me. So, holding up the RPi without breaking any of the other demos, you see as I rotate the accelerometer, it changes. There's quite a different programming model with these devices. You end up initializing an I2C port and putting a wrap around it in the NetMF case. In NetMF, it's not an I2C device you're connecting to, it's a port, and then you need to put a wrap around that to let you talk to the individual devices, change the speed, and address them all. So slightly different programming models, but it all works pretty smoothly. Stop. Another one bites the dust. So if we now flip back to the slides. So you're going to have to connect these things. There's some DIY protocols you can use. Just open a TCP port, squawk some bytes at it, and shut it down. Often that's the only choice you've got. If you've got devices which are HTTP challenged, sometimes it's just TCP. Sometimes it's even just a serial protocol, which makes it quite interesting trying to aggregate data from it. You've got HTTP, but with the overheads. You might have HTTPS, but that's going to be interesting. Microsoft deployed a bunch of new certificates to the Azure Service Bus, which broke my NetDuino 3 connectivity. There was something about the certs which the TI wireless chip inside the NetDuino 3 Wi-Fi just didn't understand. So I actually had to change technologies for accessing Azure Event Hubs about 2 weeks ago, maybe a wee bit longer. So you've got AMQP, which is the protocol, which is the guts of Service Bus. It's pretty good. It can do both encrypted and non-encrypted versions if you've got devices which are a bit processor challenged. And it spins out of the financial trading market, so it's pretty lightweight. It's bytes of overhead rather than, in the case of HTTP, tens or even hundreds of bytes of overhead. For a wireless network, around your person, you've got Bluetooth low energy. Works pretty well, but how many of you have ever had Bluetooth work first time? You've jumped into your car kit's fired up, and never. I personally have never had a positive experience with some of these technologies. Or you can use the proprietary standards like these NRF 24 devices, which I use. They're actually inside quite a lot of game controllers and mice and things like that. Those chips are 10, 15 cents a pop. There's other technologies around, like Wi-Fi, but you've got to appreciate that you're going to be in quite a noisy environment if everything's talking Wi-Fi, and quite a hackable environment, though you shouldn't rely on security by obscurity. And then 6LoWPAN and XBee. So, how many of you ever used an XBee chip? It's like flashbacks to the 70s. It's Haze AT commands if you use it one of the ways it's supported. Then we've got wide area networks, wired networks, 2G, 2.5G, 3G, whatever buzzword compliant G. Part of the problem is, though, for hobbyists, that 2G and 2.5G devices are still reasonably priced. They're like 30 or 40 bucks for a board, goes on top of your Arduino. A 3G board is a thick end of 70 bucks, which is pretty expensive. There are actually some Arduino boards out which will give you satellite connectivity, which is pretty cool. But I'm struggling to get the finance committee to approve that purchase. In Australia, I think it's Telstra has turned off their 2 and 2.5G networks, so I wouldn't be building any large deployments on that, particularly in Australia or New Zealand anytime soon. So, we've got a problem with securing these things. We've got these devices sitting out in the field. They're not talking to a vast number of servers, they're talking to a specific server. We've got to make sure that the data is kept private, and we've got to make sure it's not tampered with, which requires cryptography, which requires processor power, power to run the microcontroller, and then often results in heat, which is a problem. We've then got to see whether people have been tampering with both the device and the data. Yeah, at one thing. You can hold a cigarette lighter in front of a fire detector and see what happens, or you can physically dismantle it. I work in an industry which is quite security conscious. I take stuff home and pull it apart to see how it works. So how many of you as children pulled something apart to see how it worked? How many of you as children pulled something apart to see how it worked but couldn't get it back together again? How many of you considered that experiment a success? Right, I'm among fellow dismantlers. So we've got a problem as well. We want to be able to prove that the data came from the devices. More cryptography. We've got to ensure that these devices can tell us when they're having a bad day. But the problem is those Wi-Fi chips, they only allow two connections for HTTPS concurrently, and I think like 6 or 8 concurrent TCP connections. So how's your poor little device going to call for help if it's getting a denial of service attack and it's only going to take 8 connections? And it can't. In the Internet of Things, you can't hear your devices scream. Well, so we've got a problem. Even if you manage to get a free port, you could do the equivalent of a zip bomb attack, send messages to the device which result in a huge message being extracted on the device and consuming lots of memory, and suddenly it's all over. I've worked on a project with Hamilton Jet. They build these large water jet motors for oil rig tenders and car ferries, those big car ferries they make in Tasmania. I worked on the upgrade software. They had an application which needed upgrading, and then this software talked on a CAN bus to the devices and put new software into them. I did smile when I read it because it said, please ensure the vessel is firmly attached to the wharf before uploading. My first thought was, wonder how they discovered that. So part of the problem when you look at this Internet of Things is ensuring that the person who's running it is the person you know and trust. You might have devices uploading data, but then people can derive interesting insights from this data, so you need to be very careful about who's managing it. I had a sensor strapped to the back wall of my house with a microphone on it. You could tell pretty reliably when my kids got home from school and my wife got home because of the noise levels. It was next to the trampoline, and it's one of those cage trampolines, and it turns into a cage fight between my son and my daughter, and they'd start fighting, and then you could see the noise levels go up. This data, imagine what you could do with a Fitbit transmitting in real time. Just dwell on that for a while. These devices are going to give organisations and attackers unprecedented access into your personal life. So we need to ensure that whoever's getting at the data is people we trust. So these are very sad books. The one on the left, Source Code in C. When that first came out, DEFARS regulations meant that you couldn't export C implementations of certain crypto algorithms from the States. It was 20 years ago I bought my copy of that. I typed them in by hand. It takes a while to type in some of those algorithms, and just one fat-fingered slip and you're screwed. That book is great. It has a couple of chapters at the beginning which tell you about cryptography from the point of a mere mortal, how the algorithms work with plain English and human-friendly expectations. You don't need a beard and sandals and shorts to understand what's actually going on under the covers. And then the book on the right is how to take those algorithms and apply them properly, because most cryptography is not balked because of the algorithm, it's balked because of the way that it's deployed and used. How many of you have seen the classic picture of Tux the penguin, which has been run through AES EBC, which is not seeding every following packet with the contents of the previous packet, and you can actually see the outside outline of Tux, the penguin, in the JPEG. It's a big problem. These devices are only sending little chunks of data, and you know what the data is, so you've got to be fairly smart in how you secure it on the wire and in the air. So we've got some hobbyist things, Arduinos, Netduinos, devices like that. So there are some online hobbyist data systems. I use Xively. It's free. It means that the kids can use it and they can play around with it. So I'll just pop these into the audience. So please don't unplug anything. So these are two Arduinos. They're like $15 each. They're measuring temperature and humidity. So if you just pass them around the audience. The protocols involved. usually HTTP or TCP or MQTT. In the HTTP land, you've got some choices. In Xively, you can do it with HTTP with JSON, HTTP with XML, or HTTP with CSV. Comma separated values is really good because it sets the lowest common denominator for processor capability. We've got some protocols going. I'm going to overrun a wee bit because I had a lot of setup to do. TCP and so forth. We've got security via TLS using API keys. These API keys are often sent in clear text, which sort of defeats the purpose of them. So here we go. My laptop, 7. So the sensors that you're playing with are sending data to there, and it's then being uploaded to Xively. You'll see that device 2, a few seconds ago, device 3, a few seconds ago. So that's the one with the 2 AA batteries. So you'll see it started sending data, and then if we look at this one, this is actually my daughter's bedroom temperature. Over the last 7 days, you can see that we've had the heating on and off, and then we've had different levels of humidity. So really simple, works pretty well. And with this wireless system, you can move the devices around. Slides. So there's the code. Code is pretty simple. You just open an HTTP port, shove some bytes at it, and some magic happens. So, Azure, massive scale. 10 million devices, million events a second. You split your inbound, you use queues for telemetry. Everything's secure by default. You have to try very hard to screw up the security. Everything is SSL or encrypted by default. There is resumptions and bits and pieces coming. There's a selection of open source device agents which let you build clients running on the different versions of Nix and other common real-time operating systems. You can do HTTP in, which broke on the NetDuino. You can do AMQP. You can run MQTT, which is the IBM donated protocol, or you can build a gateway which runs in the cloud in front of Azure to let you submit stuff that Azure might not necessarily want to deal with. So on the far left, you've got devices with libraries and service gateways running on people's premises. They then get uploaded into the hub. You've got provisioning APIs so that when you start turning on your millions of devices, they know who they are and they get the right crypto keys and so forth. And then on the far right, you've got visualization tools where people can use Power BI and Excel and machine learning and so forth to analyze them. So this is some code from a .NET Micro Framework device to upload data to the cloud. And we'll just start setting the demo up here. So I've got a NetDuino 3 Wi-Fi here running, uploading temperature data. The code's not huge, works pretty well. There's like a JSON netmf, so I could actually do it without string concatenation, but string concatenation meant I could keep the size of my binary smaller. You can do it from Windows 10 with the baked-in libraries, which is pretty cool. Similar to, well, exactly the same as the desktop version. I'm using Azure Service Bus Lite, which is a really cool open source product by Paolo Paterno. I hope I haven't butchered his name. Which lets me have the same code base on my Pi and on my NetDuino. And then, if you're feeling really keen, you can do it with JavaScript. So, here comes the demo. This is a scenario which was inspired by Rob Tiffany saying one night that he was drinking a nice New Zealand wine. And I got up that morning, and it was cold. And there was frost on the ground. And I thought, well, vineyards, they need a frost fan. And if you're driving out to Waipara, you'll see that there are lots of these big windmills in the paddocks, and they use them to circulate the air down and break the heat temperature inversion layer and stop the plants from freezing. So I have a vineyard. I have a fan. It's a USB fan. I chopped the plug off the end of it. It's normally sitting on the side of your monitor. And I have some temperature acquisition equipment, so we'll take a look at that. This is it here. So here's my RPi, my fan, and I've got some ice water to simulate frost, so we'll plunge the temperature sensor into there. So if we now flip back to my PC 7. Now this is Service Bus Explorer, which is a great tool for poking around in your, ignore that, poking around in your Azure environment. So if we now create a listener to see what that little device is uploading. So now we're uploading data, and if we flip to here to make sure I'm not kidding you, it will upload some data in 30 seconds or so. So there we go. You can see the temperature's now going down. It's 3.8 degrees in that cup of water. The Brin carbon-based learning unit has now decided that it's time to send a message to the frost fan to turn on. So we'll visualize this as Azure Machine Learning doing its thing. I'm saying turn on at 50%, and we're away. So there we go. That message went from, whoops, better stop that. From temperature data went from there to Australia and was being rendered and collected from an event hub. I then had a service bus connection for command, so splitting the command and telemetry channels. It then used a MOSFET, a MOSFET switch to turn it on and off, which is this beast here, and it was driven by my RPi there. So just to prove that I wasn't kidding you, we'll do that again. So start. Oh, I'll turn that off. And then I can stop it. So the carbon-based learning, I'll just push that forward a bit, has worked out that now the frost issue is gone, and the frost fan now turns off. So telemetry and command channels split. It's important. It makes it a lot easier, and it's part of the learning process. Because so start small. Deploy a few devices. Start with tens of devices, not thousands of devices, because there will be some learning experiences which will pain you greatly and embarrass you a lot. Grow it as you come to understand, because the insights that you get at the beginning will be greatly different to what you originally expected. Managing device identity and updates at scale is hard. I built some devices to go in shops, which downloaded images from Azure Blob Storage, bad times. You need to think a lot about how you're going to manage these and operate them in the field. So, in summary, have some fun. $25 for a Fez Lima device running .NET. It's most probably not going to be a day job, but just have a laugh. Build something with your kids. Build a robot. Just build something fun. Microsoft is a player. There is no one with the number of data centers which can ingest and analyze the number of data realistically out there. Microsoft is along, and based on its new worldliness, it will play nice with others. On my demo, I've got Arduinos, NetDuinos, Raspberry Pis. I could have put a Galileo running Nix and a BeagleBoard. It's all open, and you must play nice with others. It's the only way that this technology is not going to get poisoned. So, pitch for CodeClub. I'm one of the founders of CodeClub. We teach kids how to program. We need more volunteers. We specifically need more female volunteers because our Code Clubs for girls go really well. Microsoft New Zealand is a sponsor. They gave us $6,900 to buy some kit. We have these boxes of kit for labs. And we have courseware in Scratch, Python, and HTML. And I run a series of Internet Things courses done with NetDuinos, C#, and Visual Studio. I find Visual Studio a great tool to teach with because you use your language. You say, you are now talking to an output port. So they start typing output, and then it pops up with output port, the IntelliSense. And then you go, it's an LED. What do you want to do with it? You want to write to it, so they go LED dot. And then write pops up. It makes it a really great tool for teaching and discovery. So, there are some related sessions. Some of them have passed, but I strongly suggest you go to them. I was personally quite looking forward to going to the Hackable, Internet of Hackable Things session, but had to set this up. So, I'll be having a few beers, some resources, and fill out your session evals. Thank you very much.